Hello students, Mr. Danahauer here. Today we're going to be talking about states of matter in chemical reactions. So at this point you should feel comfortable with the basics of chemical reactions, like where the reactants and products are, and even predicting products for some of the reactions, and then of course being able to balance those reactions. But one thing that we haven't discussed much is how do we know the states of matter for chemical reactions, for the substances, the particles in chemical reactions? Because let's be honest, there's a whole bunch of different substances we'll see in chemical reactions. So how do we know if they're a solid, liquid, gas, or aqueous? And that's what today's lesson will be about. So first of all, there are 4 states of matter, typical states of matter in a chemical reaction. And we use a letter, a lowercase letter, in parentheses, and usually italicized, which is hard when you're actually writing, but if you're formatting it in a document or something, we usually italicize those. So the 4 states are a solid, which we denote with an S, a small s in parentheses. Liquid is L in parentheses, G, gas. And AQ, that's an AQ, not an AG. AQ stands for aqueous, and that means the substance is dissolved in water, okay? So we're going to see for all substances, we're going to need to determine what phase of matter they are in a chemical reaction. First of all, why do we do this? States of matter in a reaction are not always necessary. But if you think about a reaction, if we're going to go repeat a reaction, and so we're maybe reading a scientific journal about a new reaction that's discovered, or a scientist was running a reaction, and we don't know what phase of matter each substance was in, then we'd have to assume that. And so basically telling the phase of matter just gives us a little bit more information about a reaction. And so if I come here and I just have a couple of examples. So this first reaction, what kind of reaction is this? Decide that really quick. If you said combustion, because you have O2 as a reactant, that's good. And remember, if we're combusting a hydrocarbon, this is our fuel source. C3H8 is propane. It's what you have in your, most of you probably have in your barbecue grill, right? And so we're combusting that with oxygen, and of course our products are going to be CO2 and H2O. Now, in this reaction, you can see all of the substances are gases, and that's shown here. Propane is a gas, oxygen is a gas, carbon dioxide and water are all gases in this reaction. Water is a gas in a combustion reaction because it's hot and it vaporizes as soon as it is formed in the chemical reaction. And that makes sense, right? We don't see water like dripping off of out of a fire whenever it's burning because it's vaporized. Now, when we see those phases of matter, it helps us go, oh, I don't really know what C3H8 is. Maybe you don't know what that is, but you can tell from this formula, from the denotation, that it's a gas. And so we're combining 2 gases together here, and we're producing 2 gases. Again, it just gives us a little bit more information. Now, here's another one. Again, what kind of reaction is this? Think about this here real quick. Okay, if you said single replacement, you're right, because we have a metal here, and we have an ionic salt or ionic compound, and my aluminum and my copper switch places. All right, and we have the sulfate still there as our anion. Now, let's look at this reaction. I have solid aluminum, okay? And then I have aqueous, copper 2 sulfate. And that copper 2 sulfate, that means it's going to be dissolved in solution. So this helps us because if, copper sulfate is a solid ionic compound. I can go back and get some out of the chemical room, and it's a blue solid. Now, if it was solid and I put solid copper sulfate with aluminum, we're not really going to see a reaction. So in this case, it's really important to know that the copper 2 sulfate has to be dissolved. It has to be aqueous in order for this single replacement reaction to actually happen. If we put solid copper sulfate with aluminum, there's no reaction that's going to really take place. Okay, so just give us a little bit more information about what's going on. So how do we know? How do we know what state of matter things are in? We'll start simple. So let's go ahead and start with the elements. You can see on this periodic table, most everything on the periodic table is going to be a solid. We have a handful of gases, and on this periodic table, those are in yellow. And then we have 2 liquids. And now remember, these are all just things that are elements, meaning they're by themselves, but that does include the diatomics. And so we'll look at those in just a second. But you can see, for example, if we ever have a metal in a chemical reaction, you can see remember that dividing line kind of slides right down at an angle right here. Aluminum's in the top corner of the metals there. And all those metals are going to be solids at room temperature. Remember, this is always, we're going to assume room temperature for these substances. But remember, the reactions can happen at all different temperatures. And just like in a combustion reaction, energy can be generated, thermal energy can be released, and that can change the phases of matter like water. So we do have to consider that. But for most reactions, we're just going to assume it's happening at room temperature, all right? Now, like I said, all metals are going to be solids at room temperature with the exception of one metal, and that's going to be liquid mercury. Okay, we have to remember that one. If you ever see mercury in a reaction, and of course, you might see that on a quiz or a test, you might see mercury as a part of a reaction. And we have to remember that mercury, when it's by itself, is going to be the liquid, and that will be the only metal that we will ever put an L for liquid for its phase of matter. All the rest are going to be S for solid. And then let's look at our nonmetals. Okay, metals, solids, except for mercury, liquid. And our nonmetals here, let's, of course, all of our noble gases over here, all of our noble gases are gases. That makes sense. We call them noble gases because of that, okay? And then the rest of the nonmetals, we want to think about our diatomics first. So if we have, what are our diatomics? Our 7 diatomics are H2, we jump over here, N2, O2, F2, Cl2, Br2, and I2. And remember, those make a 7, and there are 7 of them on the periodic table. Another way that you can remember that is using Hofbrinkel, or some say Brinkelhoff, however you want to say that. Come on, whiteboard, come up for me. Just a second here, and my whiteboard is slowly opening. Okay, well, that's opening. Let's come back here. For our diatomics, for our diatomic molecules here, all right, remember those are always, whenever we find them in their elemental form, they're always going to have a buddy system. They're going to be paired with themselves. So we have H2 here, N2, O2, F2, Cl2. Now, there are 7 diatomics. The lightest 5 of those, okay, the least massive 5, are going to be gases. So hydrogen, gas. Nitrogen gas, oxygen gas, fluorine gas, chlorine gas. Those 5 of the 7 diatomics, the 5 are gases, the lightest ones. As we get heavier, okay, there's a tendency, not always, but a tendency for substances that are heavier to be more likely to be a liquid or a solid at room temperature. Okay, and so lighter elements, or those diatomics are gases. Then we get to bromine. We're getting a little bit heavier. So Br2 is bromine in the diatomic, and it's a liquid. And then iodine is our 7th diatomic, and it's heaviest of those 7, and it's going to be a solid. Okay. So again, the first 5 gases, 6th one, bromine, is a liquid, and the 7th one, iodine, of the diatomics is a gas. Sorry, a solid. Okay, let's see if that whiteboard finally came up. So again, if you're having trouble remembering your diatomics, just remember Hofbrinkel or Brinkelhoff. H, O, F, Br, iodine, and then chlorine, Cl, all right? And so again, those are our diatomics, H2, which is always going to be a gas, okay? O2, which is also going to be a gas, F2, and we could keep going here, right? They're all going to be diatomics, going to be a gas. The only exception, I don't remember what color, but bromine is going to be a liquid. That's in little L. And iodine is going to be a solid. So that would be a handy little cheat sheet to make for yourself until you get comfortable using these and remembering those 7 diatomics and their phase of matter. All other elements, guys, as we can see back here on this periodic table, all right, all other elements are going to be solids. So recap, we have mostly solids. All metals are going to be solids except for mercury is a liquid. Bromine is a liquid, one of our diatomics. There's only 2 liquids that are elements at room temperature. And we have a handful of gases, including our noble gases and our first 5 diatomic molecules. Okay, so fairly straightforward with that. And I just put in red, don't forget the diatomics because they're always going to be found as a pair. And it's really easy when you go to write oxygen in a reaction, it's really easy to just write an O and to forget that it's actually a diatomic. So you must remember those diatomics. Okay, let's move on to molecules. All right, so we just talked about the phases of matter for elemental substances when we just have one type of element, whether it's a diatomic or just by itself, like a metal. What about molecular substances? Remember molecules? We call molecules substances that are bonded covalently, and usually that's metal, nonmetals and nonmetals combined together, sharing valence electrons, right? Now, if we, this is a little more difficult. The states of matter for covalent compounds can vary greatly. We can have, lighter things that are a gas at room temperature. We can have lighter molecules that are a liquid or even a solid at room temperature. And we can have heavier molecules that are a solid, liquid, or gas at room temperature. You might remember when we talked about bonding and properties of different bond types, we do know that things that are polar covalent are more likely to be a solid or a liquid at room temperature because of those intermolecular forces kind of holding them together. And things that are nonpolar are more likely to be a gas at room temperature because they don't have as strong of intermolecular forces holding them together. They don't really want to stick together as much. So it's easier to vaporize them. But here's the bottom line. There's a handful of substances that it would be molecular substances that would be good for you to know. But we're, in general, in our class, I'm not going to give you some covalent compound that we haven't seen before and say, what phase of matter is it? If you do see something like that on an assignment or whatever, you should just say, Mr. Danhauer, can you let us know what that is? Because I'm not going to expect you or hold you accountable to memorizing the different phases for all of these hundreds and thousands of different molecular compounds, okay? So which ones should we remember? CH4, methane, super common substance, the smallest hydrocarbon, very, very common in all kinds of processes, okay? Manufacturing processes, biological processes, all kinds of biochemistry results in methane. And so methane, CH4, is a good thing to know what it's called, methane, the formula, CH4, and that it's a gas at room temperature, okay? NH3 is another one. What's this called? NH3 is ammonia. Ammonia is also a super common molecular compound, so it's a good thing to know the name, ammonia. Formula NH3, and it's usually a gas at room temperature. However, it does dissolve in water readily, like easily dissolve, and so we can also find it aqueous as well. And so it's good to know that some of these simple ones. Carbon dioxide, of course, is a gas at room temperature, and then water, H2O, is a liquid at room temperature. Be careful with water because remember, water is a liquid and in its standard state at room temperature, but it can easily vaporize, right? Can evaporate or vaporize at room temperature as well. And in combustion reactions, there's enough energy to vaporize it. So we just have to remember what's going on with the reaction, and we can think in general, what is it going to be, but are there some exceptions? And of course, there's always some exceptions to some of these rules that we're talking about. So I would say these four would be good to remember. In any other molecular compound where it's nonmetals combined together to form a molecule, I'm not gonna ask you to tell me the state of matter for it. Okay. Now ionic, I saved ionic for last because you do need to be able to determine if an ionic compound is what phase of matter is it in. And there's a few rules we're going to follow. And ionic compounds by themselves are always solids at room temperature. So if I have any ionic compound that's not in water, okay, it's just by itself, it's going to be a solid. All ionic compounds are solids at room temperature, okay? However, if an ionic compound is with water, meaning I have a beaker of water and I put some copper sulfate or some other ionic compound in that water, it might dissolve and be aqueous, or it might not dissolve and therefore it will stay a solid and it'll just be a solid in the bottom of the beaker with the water in it. So if an ionic compound is in water, it can be S for solid or AQ for aqueous. If it's soluble, it dissolves, so it's aqueous. If it's not soluble, it does not dissolve, and so it is solid. So that begs the question, how do we know? How do we know if an ionic compound is soluble and it will form an aqueous solution or insoluble? This is where the solubility table or solubility rules comes in. Now, I'm going to show you that in just a second. So one thing to keep in mind, back to my question here really quick. How do we know if it's with water? That's the first question. And how do we know if it dissolves? Because in the reaction, maybe there's a description of the reaction and it tells you, it says aqueous copper 2 sulfate is combined with aqueous potassium chloride and it forms whatever. Now it might tell you that, but what if it doesn't? How do we know? Just by looking at the formula. So a couple of rules we can follow. Number one, most single and double replacement reactions happen in solution, meaning they happen in water. The ions have to be separated from each other, dissolved. That's separating the ion. When you dissolve an ionic salt, you're separating the ions from each other so they can interact more readily. And so usually, so the first thing you should do is look at what kind of reaction do I have here? If I have a single or double replacement reaction, there's a good chance that there's water involved. And for our purposes, you should just assume if you have a single or double replacement reaction that it's happening in water, in solution. Okay, so in single and double replacement, water is present. Part two here, other reaction types might occur in water, but in general, you should assume that they're not happening in water. For example, if you have a decomposition reaction, a synthesis reaction, or a combustion reaction, assume that those are not happening in solution, meaning they're not happening in a dissolved solution or in water. And so unless it tells you otherwise, okay, unless it tells you otherwise. So single and double replacement, assume there's water present. Decomposition, synthesis, and combustion, assume that nothing is going to be in solution for those. Okay, we're going to just have like solids, liquids, or gases, no solutions. Now, I'm generalizing stuff because this is general chemistry. So you have to remember that there are many, many more principles that go way beyond what we're talking about. But we have to start at the bottom level. We've got to start at the basics and build that foundation before we can understand more complex stuff. Right? So you take AP chemistry, higher level chemistry, you'll learn more about this stuff. We're just getting you the basics here. So we need, if we have an ionic compound, we need some kind of a cheat sheet to tell us if it's soluble or not. Does it dissolve or not? Remember, some ionic compounds dissolve and some don't. So how do we know? And that's where the solubility rules comes in. And I keep using this term salt. Any ionic compound can be referred to as a salt, like an ionic salt or just a salt. I think our brain goes, oh, table salt, sodium chloride, that's salt, right? But it's kind of adopted that name because it's an ionic compound. And really, all ionic compounds can be referred to as salts too. Another term you'll hear used with them is electrolytes. So a lot of ionic salts that dissolve are also electrolytes. All right, so anyway, back to this. The solubility rules are basically, if we take all the ionic compounds that exist, or at least all the common ones, 50 or 100 of those, and we say, okay, let's put in a pile, let's put all the ones that dissolve in water, and then let's take all the ones that don't. And then how do we know? Is there some pattern here? And there are some patterns. And so people have created different ways to visualize that or disseminate that information. This is one chart that helps us determine if an ionic compound is soluble or not. If you go Google solubility rules or solubility table, you'll find a whole bunch of different formats. Okay, there's all kinds of different formats. Some of them are super simple and they just say these are insoluble and these are not. And others have an entire chart with the amount that they're soluble and stuff. And so you can find it expressed in lots of different ways. This that I have up for you right now is what we will use for our class, and it's what you will have on tests and quizzes to use in assignments. And so while you can use any solubility chart to determine the solubility of an ionic compound, this is the one that you'll be given as a reference whenever you take quizzes and tests. You do not need to memorize the solubility rules. You do not need to memorize those. If you memorize some of them, that's great, but you don't need to. So how does this work? Remember, in an ionic compound, we always have a cation and an anion. And we're always, in this chart, we're always going to start with our anion here. And so we would find the anion that we're looking for. And then whatever cation it's joined with, we need to see which of these two columns it fits into. If it fits into this column, whenever we, okay, this is my cation, does it fit here or does it fit here? If it fits here in this column, this is soluble. Okay, these cations are all soluble when joined with these anions. If your cation falls into this category, this last column here, then it's an insoluble compound with these anions. So let's do an example of this. Let's say we'll do sodium chloride because we know that's soluble, but let's see how the chart works here. So sodium chloride, my cation is sodium, my anion is chloride ion. So I'm going to find chloride first, and that's here. So now I come across and I see which of these two columns does sodium, the cation, which of these two columns does it fit into? Well, this column says most cations. So then we need to come over here and just make sure that sodium's not with this group. And it's not. This is silver, lead, mercury, and thallium. And so sodium's going to fit here in the most cations category. So sodium chloride is going to be aqueous. It's soluble, meaning it dissolves in water. So if you had sodium chloride in a reaction, right, come over here. Okay, so if I had NaCl in a reaction that was single or double replacement, if it's single or double replacement, remember, we're going to assume that it's occurring in water. Since it dissolves, I'm going to go ahead and put aqueous. Okay. Now, it could be solid, right? If you're in your kitchen and you're putting salt into water, it's starting out as a solid. But in general, if we're having a reaction that's single or double replacement, again, we're going to assume that there's water involved in there, and we're going to assume that the substance is in water, and therefore, in this case, it would be aqueous. Let's do another one. So how about copper sulfide? Copper, it's going to be copper 2 sulfide, all right? And I just happen to have my chart over here, so let's come look at it over here. So sulfide is here, and now I need to find copper. Where does copper fit? So here we have a list: ammonium, alkali metals, alkaline earth metals. Ammonium, remember, is the cation NH4+, okay? So that's not copper. The alkali metals are the first group on the periodic table, and the alkaline earth metals are the second group. So the first group is like hydrogen, lithium, sodium, potassium, all those in the first group. Those are the alkali metals. The alkaline earth metals are next door to that, calcium and barium, and all of those in that group. And so copper does not fit any of those. We need to check all of those to make sure it doesn't fit. It does not fit. And so it's going to fit over here with most other cations. So if I have copper sulfide in a reaction, it is not going to dissolve, okay? In a single or double replacement reaction, it's not going to dissolve. And so I'm going to put solid because it's insoluble, and it will stay as a solid because it can't dissolve. Okay. Let's look at another one. Let's see here. How about, let's do potassium phosphate. Let's do potassium phosphate. So I'm going to scoot over a little bit here. Potassium K3PO4. And we want to know, what phase of matter is this? We see it in a reaction. What phase of matter is this? All right. Let's find our anion first. Phosphate's down here. I don't know if you noticed, but as we go down, the things get less and less soluble. And so like nitrate is soluble with pretty much everything. Most of the halogens are soluble with pretty much everything except for a handful of those transition metals, okay? But as we go down, there's less and less that it's soluble with. And so it's set up that way for a reason. The things at the top are more soluble in general, and the things at the bottom are less soluble. So we've got phosphate here. Let me erase some of my sketching here. We've got phosphate here. Now we need to find, we have potassium, K. Okay, so Ammonium, nope. That's this up here, right? And that's not potassium. Alkali metals, except lithium. Now, potassium is an alkali metal. It's in the first group. So you have to remember what are alkali metals and what are alkaline earth metals, because those terms are used in here, right? Alkali metals, first group. Alkaline earth metals, second group. So this is alkali metals except lithium. So it is, potassium is included because it's an alkali metal and it's not lithium. So it is going to be a soluble ionic compound, meaning if it's in a single or double replacement reaction, it's going to be aqueous. So this chart at first seems a little confusing just because there's a lot going on, but it's pretty handy to tell us the solubility of our different ionic compounds. And this will be one of the things that you practice today as you're completing some assignments. So let's practice just looking at all of these. Oh, there's one other thing I forgot to mention because I didn't really put it in my slideshow. Acids are going to be aqueous, all right? Acids are almost always, there's always exceptions, okay? But any of the acids that we give you are going to be soluble. They are going to dissolve in water and they're going to be aqueous. Oftentimes, those are going to be in single and double replacement reactions as well, occurring in water. And so if you see an acid, which of course starts with H, right? It's going to be H something. And that you should just assume those are going to be aqueous. Okay, now let's go over here and we're just going to practice a few of these. Now, I'm not going to predict the products of these. I just want to go through with you guys and let's see if we can determine states of matter for the reactants on these. So the first one, number 28 here, I just copied this from another sheet that you might work on at some point. Now I have silver oxide, and I want to know, let's say I want to put the state of matter in here, and I'm going to do it above it because it's kind of smaller, but Ag2O. So what kind of, first of all, what kind of compound? And this is not an element, right? It's not a molecular because it's a metal and a non-metal, and so this is going to be ionic. Now I need to go, okay, it's ionic, and this is a decomposition reaction. Now remember what I told you. If it's in a decomposition reaction, I would assume that water is not present in this. It could be, but in general, we're going to get this reaction to happen or something, it's probably just going to need some heat or some other kind of catalyst maybe, but there's no water involved. And so because this is not in a single or double replacement reaction, I'm just going to go ahead and put solid because it's an ionic compound and water is not present. All ionic compounds are solids if there's no water present. Okay, let's move on. Now, again, this is an example of a molecule, right? See, it's carbons and hydrogens, the hydrocarbon. And this is, I believe this is butane, if I'm remembering correctly, but I'm not going to expect you to know this one. So I wouldn't give this to you on a test. That's either going to be a gas or a liquid, and I don't remember which one it is because I've forgotten my hydrocarbon states, at least the ones that are kind of in the middle. You guys know like octane is C8H18. That's gasoline, right? And it's in gasoline and it's a liquid. The first few like propane and methane, and those are ethane. Those are all gases. And somewhere in there, there's a transition from a gas to a liquid and then eventually to a solid as they get bigger. Anyway, that's a side note. I got a little bird walk going on. How about O2? We should know that one. O2 is elemental, and it's one of our diatomics, and it's one of the 5 lightest diatomics as we go down that row of 7. And so it's a gas. O2 will always be a gas. Okay. Let's go ahead and I'm going to erase some of this. Okay. On number 30 here, aluminum, okay, metal. This is a metal, and so if we ever have just a metal by itself, it's going to be a solid. That's an S, sorry. S there. Make this a little smaller. All right, and then nitrogen, N2, is one of our diatomics, right? And so it's one of the 5 lightest diatomics. It's going to be a gas. Okay. Keep going. So here we have, what kind of reaction is this? We have an element and a compound, and we have a metal and then a metal in the compound. We have an ionic compound and an element. It's a metal. So this is a single replacement reaction. Okay. The metal, of course, metal by itself is going to be solid except for mercury. I don't have any mercuries on here, so that's not going to come up. But you should know that mercury is a liquid. It's only liquid metal. And then copper sulfate. Okay. So here we have an ionic compound. We have to go through our decision-making process. Is this in a single or double replacement reaction? Yes. That means that we're going to assume there's water present. This is happening in solution. And now we need to go find out if this is a soluble compound or not. So if it's a single or double replacement and it's an ionic compound, go to your solubility chart and determine copper sulfate. Did we already do copper sulfate? Did we do that one? Oh, we did copper sulfide. Okay, so let's look here. Copper sulfate. Sulfate's here. Copper, okay, most cations sulfate's soluble with, except for these. And copper is not in that group, which means it fits under most cations, which means it does dissolve in water, and so it's aqueous. Okay, so we'll go ahead and put that in for the copper 2 sulfate. Aqueous, because it dissolves. All right. Okay, 32. All right, we have two compounds here, two ionic compounds. That means this is double replacement. That means water is probably present, because if we have single or double replacement, we need to decide, we're going to assume there's water, and we need to go look to see if these are soluble or not. So let's go over here. Lead nitrate, okay. Here's nitrate. Most cations are soluble with nitrate, none. So lead nitrate is going to be aqueous. Okay. And then potassium chromate there. Is chromate on my list? It is. Okay. So chromate's here. Most cations it's soluble with, except for those. Potassium's not there. So this is also going to be aqueous, right? So that's how we go about this. And you guys will have a little practice now. So hopefully that gives you enough information on how to determine states of matter. And so now you should go on and get that practice done. Have a great day and School Ridge.